U-Substitution for indefinite integrals. We're going to begin our discussion on U-Substitution by talking about integration in general. Integration is considered to be more difficult than differentiation because there are no set rules for evaluating integrals, equivalent to the product rule, the quotient rule, or the chain rule for evaluating derivatives. So evaluating derivatives is actually fairly straightforward. So if I have a problem like the derivative with respect to x of x squared times sine x, well, that's a product, so I apply the product rule. If I have the derivative of something like x squared plus x divided by x, I have a quotient, I can apply the quotient rule. Now, on this particular problem, I could in fact simplify before taking the derivative using algebra, so x squared over x reduces to x, and x over x reduces to 1. So I could avoid using the quotient rule and use algebra first to use the power rule instead. But there was always the chance to just go straight for the quotient rule and not think about algebra. So derivatives, if you recognize the form, a product, a quotient, or a composition of functions to apply the chain rule, I can jump straight to using that particular rule. Integration is a little bit trickier. So with integration, we're going to have a variety of strategies, and only one strategy might work for a particular problem. So there's no, it looks like this, so just apply this. We're going to have to go through a process to figure out which is the method that I need to use to find the antiderivative or the indefinite integral. Now, one of the most common methods of integration is called the substitution method, or U-substitution. You'll hear it frequently called. And we can think about this method as sort of the chain rule in reverse, or the method for undoing the chain rule, because remember, integrals are antiderivatives, so we're undoing derivatives, and in particular we're undoing the chain rule, which applied to a composition of functions. So let's remind ourselves of the chain rule. The chain rule said if I have the derivative with respect to x of f of g of x, so g of x is inside of f of x, the derivative was f prime, the derivative of the outside, leave the inside the same, so leave g of x on the inside, and then we multiply by the derivative of the inside, so the derivative of g is g prime of x. So we'll remind ourselves even more by doing a concrete example. This example is the derivative with respect to x of sine of x squared. So the outside function is sine x, the derivative of sine is cosine, and remember we leave the inside function the same, so cosine of x squared, and then we multiply by the derivative of the inside. So the derivative of x squared is 2x, and I've chosen to put that 2x in front. So just a basic example of the chain rule. Now let's say after just doing that problem, we were asked to evaluate this indefinite integral. So we have the integral of 2x cosine x squared dx. So remember, an indefinite integral or an antiderivative is what did I have to take the derivative of to get this integrand? Well, since we just did this derivative, the function I would have to take the derivative of is sine of x squared. Because this is an indefinite integral, I'm going to include my plus c constant. So this one was fairly straightforward, but only because I had just done this example previous to it. But now try to imagine just seeing this problem for the first time. So I have a product, so I have 2x times cosine of x squared. So I have a product and a composition of functions here. And remember, there's no set rule for integration, so it's not like there's this product rule or this composition of functions rule. What I'd have to do is try to think about what I'd have to take the derivative of to get this out as an answer. So if we just hadn't done this problem, you might be able to see that this is going to be a little bit tricky. So this process that we're going to try to formalize is called U-substitution. All right, let's look at the formal statement here. So the substitution method for indefinite integrals says that if big F of x is an antiderivative of little f of x, then the integral of f of u of x times u prime of x dx can be evaluated by finding the general antiderivative of f of u of x plus c. So this is sort of a really vague way of stating the substitution method for indefinite integrals, but here's what I want to point your attention to. You're looking for integrals of a particular form. So again, you're going to want to develop an eye for recognizing the form of an integral, or the integrand in particular. So this integrand here, what we're saying is that the substitution method works for integrals that have an inside, and I kind of say that in quotes. So I'm looking for this inside function, u of x, and then on the outside somewhere, I'm looking for its derivative being multiplied, so u prime of x. So when I have an integral of this form, so here's this u of x, I'm also looking for the derivative of u of x to be multiplied somewhere on the outside of the function and still inside the integrand. So that's what I'm aiming to find. So let's go back to that previous example. So if we were asked to evaluate the integral of 2x cosine x squared dx. So again, let's talk strategy for a second. We know the answer. We know that the answer was sine x squared. But again, we wouldn't want to sit there and play a guessing game. So instead, I want to recognize that this integrand has this form up here, where if I look at what's on the inside, so the inside function here is x squared, I can also identify its derivative, so 2x, right here being multiplied still inside of the integrand. So in general, though, we're not going to have exactly the derivative being multiplied on the outside. It's still possible to have a modification of the derivative on the outside, and we'll see examples of that. But for now, we have the perfect situation. So let's go ahead and make our substitution. So this is where the abbreviation, or the commonly known shorthand, is U-substitution comes from, because what we're going to do is we're going to go ahead and let u equal this inside function, x squared. So now what I want to do is I want to go ahead and take the derivative of u. So the derivative of u, I can write it as u prime, but what I'm going to do instead is write the derivative of u with respect to x as du dx. So the left side, du dx, equals 2x. So now what I can do is, this here, du dx, is a derivative, so I can go ahead and split this up. So what I can do is think about multiplying both sides by dx. So just a quick side note, remember that dx, this is an action, this cannot be split up. So I couldn't multiply both sides by dx if I had dx, but dy dx, or in this case du dx, this is like a noun. So I can sort of think of this as a fraction, and I can multiply both sides by dx. So these two will cancel, and I will end up with du equals 2x dx. So you might be thinking, why did I just do that? Well, what I want to do with this integrand here and the differentials, I want to move things around. I want to do a clever rearrangement so I can see what's happening. So 2x dx, I want to put those next to each other. So since 2x is being multiplied by cosine x squared, I can switch their places because multiplication has the commutative property. So I can rewrite this integral as the integral of cosine x squared, and then I'm going to put the 2x behind cosine x squared, and then I'll go ahead and put the differential dx. Now you might be thinking, why did I do that? Well, what I wanted to do is show the u substitution that I'm going to be making very clearly. So the idea is that right now, this integrand is something that I don't know its general antiderivative of right away. But what I can do is I can rewrite the integrand in terms of a different variable, that variable being u, to make it look a little bit nicer. So this integral is equal to, it's the same as cosine. So the substitution I'm making is, well, we said let's make u be equal to x squared. So change colors here. So what we're going to do is we're going to replace x squared with u, and then 2x dx here, well, that was the same as du. So my integral that was cosine x squared times 2x dx, Well, I replaced x squared with u, that's coming from this portion here, and I'm going to replace 2x dx with du because those two things are equivalent. So now, let's go ahead and make that substitution. So my integral became the integral of cosine u du. That's a lot nicer to solve here. So now I can evaluate this general antiderivative really easily. So I know that the general antiderivative of cosine u du, it doesn't matter that it's u's, right? It could be k's, it could be q's for all that matters. The u is just some variable, and as long as they match, we're fine. So the antiderivative of cosine u du is going to be sine u plus the constant c. Now, there's one additional step I'm going to need to take. My original question was in terms of x. And when I have an indefinite integral, I want to make sure that my final answer is still in terms of x. So the final step is going to be to go back and replace the u with the function in terms of x. So my final answer here has to be sine x squared plus c, which we already knew to be the answer, but this is just showing the process of using U-substitution to find that general antiderivative. So what I like to do is I like to do my scratch work underneath the original integrand, and then I even put a little box underneath it just to kind of show that this is scratch work. But all of the equal signs here are correct equal signs. This original problem was equivalent to this rearrangement, which was equivalent to this substitution using this information, and then this integral was just easier to solve. So the point of the substitution method is to create an integral that's easier to solve with the previous rules I had for finding general antiderivatives. Alright, so now let's take a look at a strategy for solving integrals using U-substitution. So I want to be careful and not call this the steps for finding or solving integrals with U-substitution because, again, just to stress, there's no set rule for doing this. So there's nothing as nice as low d high minus high d low over low squared. There's no set rule. There's just going to be this strategy that I want to keep in the back of my mind as I attempt to use the substitution method. So the first thing we're going to try to look at is in the integrand, we want to identify the u of x function. So we want to find u. Now, it's commonly, but not always, an inside function, or it could be the function that's on the bottom of a fraction bar. So if we have something that looks like a rational function or a function over a function of any kind, then it's possible for the u of x to also be on the bottom. And when looking for this u of x, you're often also looking to find its derivative or its modified derivative in the integrand as well. But that isn't always necessarily the case. So again, there's no set of rules, but the first thing we're going to try to do is find the u of x, and it's on the inside or on the bottom pretty often, and we want to also look out for its derivative somewhere in the function. Once we find that u, we're going to take its derivative, so we're going to find du dx, or I'm being vague here because usually it will be x, but we could have a different variable. So find du dx and then multiply the dx to the other side. Something else we may have to do, and we'll see an example of this, is we may also have to solve for x given the u of x function. And we'll see what that means in an example. And this is sort of a sub portion to part 2. If evaluating a definite integral, we must also change the limits of integration by substituting them into u of x. So we then do not return to the original integrand. And again, there's going to be a formal substitution method for definite integrals that will show a little bit of what I'm talking about here, but we have to remember if we're solving a definite integral that there's going to be an additional step that says we have to change our limits of integration. Then we perform the change of variables. So that's the step where we replace the function and its derivative with the u and the du respectively. Then we evaluate the new integral, and the idea is that this new integral is nice, that it's an easy thing to take the integral of, and we're taking the integral with respect to the variable u that we just changed out everything for. And then if we were solving an indefinite integral, we go ahead and replace the u with the original substitution function u of x, because we do want our final answer to be in terms of the original variable. So if it was x, we need to go back and replace u with that u of x function. So this is just a strategy for solving integrals, and this is something that you might want to go back to and refer to after we go through a couple of examples. Alright, so let's jump into an example. Here we're trying to evaluate the integral of 3x squared cosine of x cubed dx. So here what we have is we have this inside function x cubed, and we want to be able to see if we can find its derivative or a modification of its derivative being multiplied somewhere on the outside. Well, conveniently, right here in front, 3x squared is exactly the derivative of x cubed. So what we're going to do is we're going to go ahead and choose our u then to be x cubed. And that means that du dx is the derivative of x cubed, which is 3x squared. So that means that just du, the differential du, is equivalent to 3x squared dx. So again, I can think about multiplying both sides by dx. So now let's go ahead and do some grouping here. So I'm interested in making the replacement of x cubed with the variable u, and then 3x squared dx I want to replace with this du here. So let's move some things around in this integral. We're going to have the integral of cosine x cubed. So writing the cosine x cubed function first, and then writing 3x squared dx next. So just to see our substitution of variables a little bit clearer in the next step. So this will become the integral of cosine, and we're making the substitution that x cubed is the same as u. So I'm going to rewrite this as cosine u, and then we're going to go ahead and replace 3x squared dx with du. So cosine u du is the new integral I'm attempting to solve. And this one is pretty straightforward, same as the last one in fact. So the antiderivative here is going to be sine u plus c. And the very last step is, if we're solving an indefinite integral, we want to go back to the original variable. So the original variable was x, so we're going to go ahead and replace the u back with x cubed. So our final answer here is going to be sine x cubed plus c. So this here is going to be my final answer. And as I said, I like to just create a little sort of box to keep this scratch work off to the side here. So another pretty straightforward example, really similar to the last one. So now let's look at something a little bit different. So here we have the integral of x times the quantity x squared plus 3 to the 5th power. So far, we didn't have a strategy to solve something that looked like this other than sort of guessing and checking. Something like this, we do have the ability to solve for it with the methods that we currently have, but it would be quite a nightmare. So what I mean by that is what I could do here, I don't have any product rule, right? Let's just make that clear. There's no product rule, but what I could do is I could write this as x times x squared plus 3 multiplied by itself 5 times. So I could do x squared plus 3 times x squared plus 3, etc., and do all of this distributing, and then use the power rule. But doesn't sound fun at all. So that's not the strategy we want to use, and we want to think about all those different possibilities, because sometimes it will be advantageous to use some algebra first, but this one, not advantageous. But what I can do is I can think about this inside function idea. So on the inside of x to the 5th, I have x squared plus 3. So my inside function that I'm taking a look at is x squared plus 3. Now the derivative of x squared plus 3 is 2x plus 0, or 2x. I don't have exactly 2x multiplied on the outside, but I do have x. And that's close enough. It only is different by a constant, by some number. So that's what I meant by we want to find an inside function and its derivative or modified derivative. So what we're going to do is we're going to go ahead and let u equal x squared plus 3. And so du dx, the derivative with respect to x, is now 2x. So that must mean that du is equal to 2x dx. So the only problem is that I'm searching strictly for x dx. So when I manipulate my integral in just a second, so if I manipulate this, this is the integral of x squared plus 3 to the 5th, and then I'm going to put the x dx together. When I go to make my substitution, I don't want this 2 here. I want to be able to replace x dx without the 2 in front, because I don't have a 2 over here in the actual integrand. So what I can do is I can just go ahead and divide both sides here by 2. So what I then have is 1/2 du equals x dx. So now I can go ahead and make my substitutions. So this is going to become the integral of, well, x squared plus 3 to the 5th power will now become u to the power of 5. But now x dx, this portion here, is exactly 1/2 du. So now I have the integral of u to the 5th times 1/2 du. But I have this nice property of indefinite integrals that I can pull out a constant multiple, or I can pull out a constant. So let's go ahead and rewrite this as 1/2 the integral of u to the 5th du. So this is a lot nicer of an integral to solve than something like this, because I can apply the power rule here. So this would become 1/2 u to the 6th over 6. So I'm using the power rule, add a power, divide by the new power, plus c. So now I'm just going to go ahead and go back and replace u with the function in terms of x squared plus 3, and then at the same time I'll go ahead and multiply across here. So my final answer would be 1 over 12, and my u was x squared plus 3 to the 6th plus c. So that's going to be my final answer here. And it was a lot easier than doing all of the distribution that would have been required in evaluating algebraically x squared plus 3 to the 5th power, and then distributing in the x and all that. And that answer would have also been really, really messy. So this answer here is nice and concise as the antiderivative to this function here. So this is my answer, and then I'm just going to go ahead and do the same thing, leave my scratch work sort of off to the side boxed in. So this was the substitution that I made, which led to this as my final answer. Alright, let's move on to another one. So we're evaluating the integral of x times e to the x squared plus 1 dx. So here I don't have a strategy currently for solving this, so what I want to try to identify is some inside function and then its derivative multiplied somewhere on the outside. So here I have e to the power of x squared plus 1. So on the inside of e, I have e to some function. On the inside of e is x squared plus 1. Well, now the derivative of x squared plus 1 is 2x. And here's just x, which is close enough. It's only different by a constant. So I'm going to go ahead and let u equal x squared plus 1. And now I'm going to say that du equals 2x dx. So notice I skipped a step, and that's fine. You don't have to write every time du dx and then multiply both sides by dx. So you can go ahead and jump to du equals 2x dx, but the step that I would want to see is that we are only interested in x dx. So let's go ahead and divide both sides by 2, which is like multiplying by 1/2. So 1/2 du equals x dx. So dividing both sides by 2, multiplied by 1/2, I end up with just the x dx that I'm interested in. So now my integral is going to become, well, when I make the substitution of x dx is going to become 1/2 du, just like in the previous problem, the 1/2, that constant, will come to the front. So let's go ahead and jump in and do that automatically. So it's going to become 1/2 the integral of, well, x dx is going to become 1/2 du. Well, we already have the 1/2 here, so let's just go ahead and write the du. So the 1/2's in front, the du is in the back. And then e to the x squared plus 1 will become e to the u. So I'm making the substitution that x squared plus 1 is u. So now I'm evaluating 1/2 the integral of e to the u du. Well, that one's really nice to solve as well. The antiderivative of e to the u is just e to the u. So the 1/2 will come down and I have e to the u plus c. And I can't forget to go back and replace the u with the function u of x. So everything's in terms of x. So I have 1/2 e to the x squared plus 1 plus the generic constant c. So pretty similar to the previous problem, but a different type of function. So this time we were going back to the general antiderivative that we knew, the exponential function. So we're still going to have to go back and reference those previous general antiderivatives to move on and solve a little bit more complicated indefinite integrals. Now this next one. This next one might be stumping you a little bit when you look at it. So for one, it's just one function. So the idea of an inside function, really, I mean, there's no inside function other than x, and the derivative of x is 1, which is on the outside, but that doesn't help us. So what we want to do to find the integral of tangent x dx is we want to be a little clever. We want to write this so that it looks like a quotient. So that means going back to pre-cal, and we can rewrite tangent x as sine x over cosine x dx. So again, those general strategies told us that we were looking for a u. So right here in this function, there's no general antiderivative of tangent x. I can't just think, well, what do I have to take the derivative of to get tangent? We don't really know that. That wasn't one of the rules that we had so far looked at for general antiderivatives. So I want to think about any way I can use my previous knowledge to rewrite tangent, that's sine over cosine. So now that I have a quotient, I can think to use U-substitution, but instead of thinking about the inside, I need to think of what's in the denominator. So I'm going to go ahead and let u equal the function in the denominator, which is cosine x. And then ultimately what I would be searching for is the derivative of cosine x being multiplied. And well, the derivative of cosine is negative sine x, and there's negative, or sine x, positive sine x, on the top here being multiplied. So I'm going to jump straight to saying that du is negative sine x dx. So this is pretty close to what I want, except for the negative. So I want to be able to replace sine x dx with some modification of du. So let's divide both sides by a negative. Negative du equals sine x dx. So now I can think about this dx being in the numerator. So when we write the dx off to the side and in the middle, it's really up here in the numerator. So what I want to do is I want to make my substitution of variables. Sine x dx, we just said, was negative du. So we'll go ahead and put that in the numerator. And cosine x was exactly u, which is in the denominator. So I'm evaluating the integral of negative du over u. Well, let's go ahead and factor out that negative and evaluate the integral of du over u. So it's just like dx over x, because again, the variable doesn't really matter. So my general antiderivative here is negative the natural log of the absolute value of u plus c. And now I'm almost done, except that I have to go back and resubstitute in cosine x for u, so my antiderivative is in terms of x. So it's negative the natural log of cosine x plus c. So once again, to stress that there's no set formula here. So we've now gone over a couple of different examples. And in all of them, it's just going to take a lot of time and practice to start to see and recognize when we should use U-substitution, what to choose for our U. So here, a lot of students might get mixed up and think to choose sine x as the U. And then the derivative of sine is cosine, but we don't have cosine, we have 1 over cosine. So sine x dx over cosine x, we can think of it as sine x times 1 over cosine x dx. So if a student were to choose u to be sine x, the derivative is cosine x, but I don't have cosine x, I have 1 over cosine x, which if you'll remember is secant x. So I don't really have a u substitution here. With u being sine x, I have to let u be what's in the denominator, and in this case that's cosine x. So just a couple of things, and the more that you do, the more that you'll start to see the different strategy to use. Alright, and now this next example is completely different from the ones that we've been solving so far, in that it's still a u substitution problem, but we're going to have to actually do an extra manipulation here to be able to apply a change of variables. So here I have x times the square root of 5x plus 1 dx. Just to clarify, there's no other strategy I have so far that I've learned to solve this type of problem. And I know that there's an inside function, so I should think here u substitution, and the inside function is 5x plus 1. But a quick check of the derivative of that. The derivative of 5x plus 1 is 5. So I'm going to have this extra x just kind of hanging out here because I cannot, per se get rid of it when I try to find du. So let's kind of go with it for a second so we can see that we're still going to apply u substitution with just an extra step. So let's say u is 5x plus 1, and then du will be 5 dx. So right now, if I made my substitution of variables, here's what I would have. I would have the integral. Nothing gets rid of this x, so this x would just kind of be still there. And then I'd have the square root of, well, I can get rid of 5x plus 1, that's u, so the square root of u. And then dx, well, I'd need to go ahead and isolate the dx, so I'd have 1 over 5 du equals dx. So I can bring the 1 over 5 to the front of the integral, and then go ahead and put the du at the back. Alright, this does not help us at all. We have two different variables here. We want to change everything to the same variable. So what I want to do is I want to get rid of the x, and I want to make the x in terms of u. So the way we're going to do that is we're going to look right here at the fact that u equals 5x plus 1. I can solve this first equation here for x to get x in terms of u. So what I mean by that here is that I can rewrite this as u minus 1 equals 5x. So I'm just adding 1 to the other side, and then divide both sides by 5. So I end up with u minus 1 divided by 5 is equal to x. So I'm going to go ahead and replace this x here with u minus 1 over 5. So now my integral is 1 over 5, the integral of u minus 1 over 5 times the square root of u du. So you might be asking yourself, is this any easier to solve? The way that it's written right now, it looks kind of messy, but in fact, it is easier to solve, and I do have a strategy for solving it. So what I'm going to recognize here is that u minus 1 over 5 is really 1/5 times u minus 1. So how about we go ahead and factor out the 1/5, factor out the constant. So I'm going to go ahead and have on the outside here 1 over 25 because I had this 1/5, and I'm pulling out this 1 over 5 here with this 5. And now I end up having the integral of the quantity u minus 1 times the square root of u, well, that's u to the 1/2 du. So now, to solve something like this, I can go ahead and distribute. So I can solve 1 over 25, the integral of, if I distribute here, I'm going to get u to the 3 over 2. So u times u to the 1/2 is u to the 3 over 2, minus 1 times u to the 1/2 du. And now I can apply the power rule. So I end up with 1 over 25, and u to the 3 over 2 will become u to the 5 over 2 times 2 over 5, minus u to the 1/2 will be u to the 3/2 times 2/3. And then I have to remember the constant. And now I need to go ahead and substitute u back in as 5x plus 1, so I have everything in terms of x. So here I'm going to have, let's distribute as well. So we're going to have 2 over 125. So I'm distributing in the 1 over 25. So 2 over 125, u was 5x plus 1 to the 5 over 2, minus, now here I'm going to have 2 over 75. So 2 and then 25 times 3 is 75. So minus 2 over, 75. And then u again was 5x plus 1 to the 3 over 2 plus c. So this giant ugly looking thing right here is my final answer. And it was a modification of a U-substitution. So a U-substitution means that we want to go ahead and change the variable to u. So it didn't just require us to find a u and a du, it also required us to manipulate u to solve for x to make everything the same variable here. So that's another strategy of applying the substitution method. Alright, and now some assorted AP multiple choice questions. So this is number 8 of a previous AP exam. So we have the integral of x squared cosine x cubed dx. So you'll notice this is really familiar to the problems that we've been solving so far. So let's go ahead and let u be the inside function here, x cubed. Then du is 3x squared dx. We're only interested in x squared dx, so let's divide both sides by 3 or multiply by 1/3. So 1/3 du is x squared dx. So my integral here is equivalent to 1/3 the integral of cosine u du. So we went ahead and let x squared dx equal 1/3 du. I put the 1/3 in front here and then replaced x squared in dx. And then I replaced x cubed with u. And now this is 1/3. The antiderivative of cosine here is sine. So sine u plus c. And we can go ahead and substitute u back in because this is an indefinite integral. So 1/3 sine x cubed plus c. And if I wanted to go ahead and check my work, the nice thing is that I can. So I can take the derivative here. The derivative of sine x cubed is cosine x cubed times 3x squared, but I had this 1/3 in front. The derivative of a constant is 0, and the 1/3 and the 3 cancel, so I end up with just x squared cosine x cubed, which is what I wanted. So I know that this is the correct answer, and the option for that one is B. So the answer to number 8 of a previous AP exam was B. And now the integral of x over x squared minus 4 dx. So this should look pretty familiar. Here, again, I can't do any algebra. I can't write this as x over x squared minus x over 4, anything like that. I have to use a u substitution where u is the denominator, x squared minus 4, because then the derivative is 2x, and I have x dx, so it's close enough. So du equals 2x dx. I only want x dx, so 1/2 du equals x dx. So now my integral is going to become the integral of, well, x dx is 1/2 du. So we'll put the 1/2 in the front, and then we're going to have the du on top. So x dx was 1/2 du over x squared minus 4 was u. So now this is a really nice antiderivative. I have 1/2 the natural log of the absolute value of u plus c, or 1/2 the natural log of, substituting u back in, I get x squared minus 4 plus c on the inside of the natural log function. So this here is my answer, which corresponds to C again. A lot of C's again, but the answer to all the multiple choice is not C. And that's it for this one.